Okay, hello. Well, here we're going to look at the review questions and the problems in Chapter 4. If you turn to page 138, we have the review questions, and on page 139 and 140 we have the review, practice problems. I'm not going to necessarily go over every particular one, but we'll see how far it goes and how much time it goes. We'll see. I may skip a few. Okay, on page 138, we see the review questions, and let's just start with number one. Number one, explain how you would look at a two-dimensional situation so as to make them as easy to analyze as possible. Well, like we talked in the lecture, whenever we have a two-dimensional problem, we want to break it up into its components, a horizontal component and a vertical component. We solve each of these independently, and then then we can bring them back together. So question number two, what do you know about the x and the y component of the projectile's velocity when your projectile is at the maximum height? Okay, when a projectile comes out at the maximum height, at the peak, the projectile is in purely horizontal velocity and there's no vertical component. So the y component is 0 and the horizontal component is the same as the initial horizontal component. Okay. Number three, a projectile lands at a height that's equal to the height on which it was launched after a total flight time of 4 seconds. So total flight time of 4 seconds, how many seconds after launch does it reach its maximum? Well, the maximum occurs at the midpoint, so half of the total time is 2 seconds. So the peak occurs at 2 seconds. Okay, question number four. A projectile is fired upward at a velocity of 150 meters per second. When it again reaches the height from which it was launched, what is the speed? Well, when it goes up and then it comes back down, the final speed is exactly the same as the initial speed. It's just in the opposite direction. So it will be 150 meters per second going down. Number five, question five. What happens to the y component of a projectile's velocity as the projectile travels through the air? Okay, the y component starts off with the y component, and it gradually decreases until it gets to 0. Starts off large, gets to 0, and then it gets large. It gets large and large again, but in the opposite direction. So starts off, it goes 0, and then it flips back down the other way. Okay, number six. If a projectile is fired in empty space, that is, there's no planets or stars in the area, will it still follow a parabolic path? Why or why not? Now, that's a very good question. If there's no planets nearby, if there's no stars nearby, is there any gravitational attraction? Well, if we say we're far enough away from any star or planet that there is no gravitational attraction, then there will be no gravitational attraction. That means that there will be no gravitational acceleration. If there's no gravitational acceleration, there's no parabolic motion. When you fire a rocket and just let it go, it simply travels in a straight line. Okay. Number seven. In which of the following situations can you use equation 4.9? 4.9 is the range equation. In the first situation, you're shooting a basket into a basketball hoop, and the basket's up here. Can you use a range equation for that? No. The reason is because where the target is at a different elevation than where you're shooting from. You cannot use a range equation in that case. The second case is where you're shooting a soccer ball to a goal. The goal is at the same elevation you're at, so yes, you can use the range equation there. Okay, number 8. A sharpshooter tells a nervous man to hold a can at arm's length. Sounds very dangerous. The sharpshooter then says that he will shoot the can out of the man's hand. Bad idea. Don't try to duplicate this at home. The sharpshooter realizes, however, that the nervous man will be scared at the sound of the gun and will drop the can as soon as the gun is fired. In order to still hit the can, should the sharpshooter aim above, below, or at the can? This, of course, is a hypothetical situation. It would be far too dangerous to actually do this. Well, think about it. When the sharpshooter shoots, the bullet's going to go slightly down. Okay, what does the sharpshooter say? If he aims directly at the can, he knows that his bullet's going to go down. Okay. However, he also knows that the man's going to drop the can too. So, when the can falls and the bullet fall, will they fall at the same rate? Do you say yes or no? If you say yes, that's the right answer. The can and the bullet will in fact fall at the same rate. So, the sharpshooter still should aim directly at the can, knowing that when he shoots it, the man's going to let go and the bullet will then fall into the can. Okay, let's see here. Okay, number 9. Okay, number 9. Suppose the man holding the can is not nervous and the sharpshooter knows that he will hold the can even after the gun is fired. Should the sharpshooter aim above, below, or above or at, or what should he do in this case? If he's not going to drop the can, he should aim a little bit high so that the bullet will then hit the can. Make sense? Okay. Number 10, what have we ignored when solving all of these projectile motion problems? What have we ignored? We've ignored air resistance. Okay. So, okay. Go over to flip over to page 139. We have the practice problems. We have number 1 and number 2 are heading problems, and I'm actually going to choose, I hope you don't mind, but I'm going to not solve these problems. You should do these problems, match them according to what the answer says, but I'm not going to do them simply because they're very similar to actually chapter 3. And so, however, there will probably most likely be problems like this on the test. So you need to practice those types of problems, number 1 and 2. Okay, let's start with problem 3 on page 139. Okay, a ship fires at an enemy shore factory which sits behind a rather large mountain range. So here's a ship, and it's shooting a gun, and it fires. It fires at a certain angle. Okay, it's a kind of a bad drawing here. It fires its cannon, and there is a mountain range right here. And here's the factory over here. The tallest mountain is 500 this height is 550 meters high. Okay, and it stands halfway. This is a bad drawing, but basically, if this is the range, that this is halfway, 1/2 of the range. The mountain is halfway in the middle between the ship and the factory. This is the ship firing the gun. Okay. In order to hit the factory, the gunnery sergeant determines that the projectile's initial velocity must be 200.0 meters per second, and the angle here must be 30 degrees. That's what he calculates in order to hit the factory. Okay. Determine if when he shoots it, it will clear, or will it not clear, and will it hit the mountain? What will happen here is, essentially the question is, will the cannon clear the mountain and hit the factory, or will it hit the mountain and is the factory safe? Okay. So, well, what's the first thing we want to do? Well, we know this is a range equation type of situation. Okay, so we can actually use the range equation here. The range equation, remember, x range equals the initial velocity squared times the sine of 2 theta, all divided by g. Okay. We could solve for this, and that would give us the range, and at that point we could then that could then give us this distance. If we know the full range, we could then calculate what the range is, or the distance to the mountain is, because that's half the range. Okay. Once we have that, could we actually calculate? Basically, what we want to do is we want to calculate this maximum distance here, and I'll write it this way. We want to calculate y max at midpoint. Okay, we want to calculate y max at the midpoint. Okay. Now, actually, when we calculate y max at midpoint, do we have to actually know, let's think about this for a second, do we have to know the x range? Well, forget the range right now, just think of this problem. We would solve it in the y, this is a y dimension problem, in the y dimension, okay, at the peak here, wherever that peak is. What do we know about the peak right at the maximum? We know that the y component is 0. Okay, so think of this, the y in the y of v, the final squared equals the initial squared, the initial velocity squared, plus 2ax. If we look at this in the y component, in the y dimension, it would be the y component of the velocity squared equals the initial y component minus g. I'm going to change a to g, and this x here becomes y max. Okay, so that's the same equation, but applied to the y dimension. The velocity at the peak, where y max is, this is 0. So we have 0 equals, now the velocity in the y component here the initial y component is the initial velocity times the sine of this angle, 30 degrees. So it's the initial velocity times the sine, the initial velocity squared times the sine of the angle squared, minus 2g y max. We can now come and solve for y max. Notice that even though we had the range, we could have used the range equation, and we could solve for what this distance is. It doesn't really help us in determining the maximum of the y. That we can get by just looking at the y component. So I'm going to erase this equation here. And flipping this over here, we get 2g y max equals the initial velocity squared times the sine squared of the angle. And coming up here, if we solve for y max, I'm going to erase this here just to make more room. Y max equals the velocity squared times sine squared of 2 theta, sine squared of theta, all divided by 2g. Okay, so let's go ahead and take these numbers and plug these numbers into this. So what do we have? The initial velocity is 200.0 meters per second, and then we square that, and then we multiply it by sine squared of 30 degrees, all divided by 2 times 9.8 meters per second squared. Now notice from a units point of view, we have meters, this turns out to be meters squared over seconds squared, all divided by meters over seconds squared. The seconds squared cancel out. One of these meters cancel that meters, and we're left with y max in meters, which is as it should be. So now we take our calculator. Notice when you do this, what you're really doing from a calculator point of view is you're taking sine of 30 and then you're squaring that. Okay? So don't get confused. You're not taking 30, squaring that, and then taking the sine. You punch in 30. Well, depending on how your calculator is, you may do sine of 30 quantity squared if you have one of these like a TI 85, but mine's a more simple calculator, so I would punch in sine. I would punch in 30 degrees, hit the sine button, and then I square that, okay, times 200 squared divided by 2 divided by 9.8, and I get a y max of 510 meters. So what does that mean? This crosses right here at 510 meters. The mountain is 550 meters. So basically that means that the shell hits the mountain, boom, hits the mountain, and the factory is safe. So that's how you solve that problem. Okay. Okay, problem number 4. A soccer player kicks a ball from the ground and it reaches an initial, with an initial velocity of 8.2 feet per second and this angle of 40 degrees. There's the ball. How long will it take? How long will it take for the ball to reach the maximum height? How long will it take for the ball to hit the ground again? Okay, so this is a time question. So here the ball goes up and it hits the ground. The question is the time to the peak. What is the time to peak, and what is the total time? Well, we know that the total time is equal to simply 2 times the time for the peak. Okay, so if we can solve for the time for the peak, then we have the problem solved, basically. Okay. Well, we know that for the time situation here, that the initial velocity in the y dimension, is the initial velocity times the sine of this angle. Here's v. That's equal to VO, the initial velocity. The initial, think of in the y dimension. Okay, in the y dimension, we have that the initial, that the final velocity in the y dimension is equal to the initial velocity in the y dimension plus the acceleration times time. Okay. Now, since this is a y dimension, this is a minus g. Okay. And we know that right up at this point, the y velocity is 0. So this, we can say, is 0. The initial velocity in the y component is this, minus g, and this is a t, time to peak. So we can solve for this. G times time to peak equals the initial velocity times sine of the angle, and we can solve for the time to peak. Time to peak equals the initial velocity sine of the angle all divided by g. So we can come in here and just plug in the numbers and we get 8.2 feet per second times the sine of 40 degrees. I'm writing kind of quickly here. Now g here is 32. 32 feet per second squared. I hope you can see that. And if I plug that number in, I get 40 sine of 40 times 8.2 divided by 32, and I get 0.16 seconds. So the time to peak is 0.16 seconds. That means the total time is twice that, or 0.32 seconds. Okay. So I hope that's clear. Now you might have thought about this. Just to give you an idea, you may have thought about this. You may have thought, well, I'm going to use the equation to solve for this. I'm going to use the equation in the y dimension, x equals VOT plus 1/2 AT squared, and apply this to the y dimension, and I would get y max equals the initial velocity in the y dimension times time minus 1/2 GT squared. Okay. You could have said, well, I'm going to use this equation. Could you have used this equation? Actually, yes, you could have. Would it have been more difficult? Yes, it would have. But it should give you the same answer. How would you have done it? Suppose you had started off saying, I'm going to use this equation to solve for t. It should work. It's just a little bit more cumbersome. Normally there's two ways to do this. How would you have done it? Notice that the y the y component would be VO sine of theta times t minus 1/2 gt squared. Okay, now one of the problems is we don't know what y max is. So how would we be able to solve this? Notice that in order to really, if you knew what this was, then you could plug this number in. If you knew what this was, you know what this is, you know what that is, you could solve for t using the quadratic equation. But you first have to know what y max is. How would you know what y max is? Well, you could solve this equation squared equals the initial, that the velocity in the y squared is the initial velocity squared minus 2g y max. This is equal to 0. You take this equation and you solve for y max. Then you plug this y max into here, and then you solve the quadratic. It would work. It's a very time-consuming step. It's a two-step process. You could do it. You would get the right answer. It would work. How would you actually, suppose you did that and you solve for y max, how would you actually solve this quadratic? Let me just show you, just from purely a mathematical point of view. For quadratic, you have to set it equal to 0, so I would move this to the other side, so I'd have 0 equals, and I'm going to put it like this, minus 1/2 gt squared plus VO sine theta t minus y max. Notice this is in the form of 0 equals ax squared plus bx plus c. That's a quadratic equation, so you can then say where x is now t, where I can say x, the solution is x, or in this case t, is minus b plus or minus b squared minus 4ac square root of all divided by 2a, where a is now this number, b is this, and c is this. You can do it. You can plug it in. It will work. It's just time consuming. Okay. Okay, that's question 4. Okay, question number 5. What is the range of a cannon that flies its cannonball with an initial velocity of 355, initial velocity of 350.0 feet per second with the angle here of 35 degrees? Okay, well, this is just, what's the range? It comes up here and here, from here to here. This is the x range formula. X range from here to here is, as we know, VO squared times the sine of 2 theta divided by g. I simply take the initial velocity, plug it in here, take this angle, plug it in here, and I solve for the range equation. I'm not going to do it, but it's just a straight application of this range equation. That's number 5. Okay, number 6. Number 6 is actually a little bit similar. Number 6 on page 140 is kind of similar. You have a soccer player, and exact same kind of geometry here. And this time, the soccer player wants to kick. Soccer player A is kicking it to soccer player B. He knows what the range is. The range is 31 meters. Must have a radar gun or something. Must have in order to figure that out. He knows what the range is. The question is, what is the initial speed? And he knows he's going to kick this angle at 45 degrees. That's pretty accurate there. The question is, what is the initial velocity he must have to get it there? Well, this is an application of the same range equation. In this case, you're going to take the range equation and simply solve it for v. So I'm going to erase this here.